bar magnet as an equivalent solenoid. Actually, we have already studied these two has the same field lines, right? A current carrying straight solenoid behaves like a bar magnet. This was already shown through the magnetic field lines. A study of magnetic field lines around a solenoid carrying current and magnetic field lines around a bar magnet shows that both field lines has the same property or has the same shape or has the same structure, and from that we can say that the solenoid acts like a bar magnet. All the properties of bar magnet are applicable in case of solenoid also. Now we are going to show that field on an axis of a long solenoid, field at a point on the axis of a long solenoid carrying current has the same form or has the same expression as the field due to a bar magnet at an axial point. Already we have deduced that the reduced expression for the magnetic field at an axial point of a bar magnet. Now we are going to calculate a field on an axis of a long solenoid. Now let us consider a long solenoid. Let us say consider a long solenoid of radius A and length 12, having n number of turns per unit length. This is a long solenoid, and this dotted line is the axis of the solenoid, and this is the radius of the solenoid A, and let us say this is the center point. This is the center point O of the solenoid, and this length is L, and this length is L. Therefore, total length of the solenoid is 2. And this dotted line is the axis of the solenoid. To calculate the axial field, that is field at a point on the axis, at a point P, let us say this point is P, which is at a distance R from the center of the solenoid, and also this point is on the axis of the solenoid, right? Now the distance of the field point P from the center of the solenoid is R. Now to calculate the field at P, we consider a circular element of thickness dx of the solenoid at a distance x from the center. That means let us consider this length. This is an infinitesimally small thickness of dx, and which is at a distance x from the center of the solenoid. That means now we are taking a very small thickness of circular coils, right? And these circular coils has the number of turns of this elementary circular coil is into dx. This is the number of turns, because we have considered the solenoid has smaller number of turns per unit length. Length of the solenoid we have taken is dx, therefore number of turns in this elementary solenoid or in this circular loop has n into dx number of turns, right? Now the magnetic field at the point P, due to this circular element of thickness dx is what? Let us say that is dV, and dV we have already deduced an expression. If this is circular loop, then at a distance r, if the radius is a at a distance r on the axis of the circular loop, field B is equal to what? We have reduced this expression, mu naught n I s square divided by 2 into s square plus r square to the power 3 by, is it? This can be written as mu naught by 4 pi. Then we have to put here 2 pi n I s square divided by s square plus r square to the power 3 by. This was our expression for the field due to a circular coil on the axis, and we have already told that the direction of the field was in this case this was away from the coil. If the current is anti-clockwise direction from the field point, if you see that current is in anti-clockwise direction, then field will be away from the coil. If the current is in clockwise direction from the field point, then field will be into the coil, right? Now, therefore, the field at P due to this elementary circular coil will be equal to what? Will be equal to mu naught by 4 pi 2 pi. Now n is the total number of turns. Here number of turns is n into dx, and I is the current flowing through the solenoid. Therefore this will be I, and A is the radius here, also a square divided by a square plus this length is r minus x, therefore this length will be equal to a square plus r minus x whole square to the power 5. Now this is the field at the point P due to this elementary circular loop. We consider P point is far away from the center of the solenoid. That means R is much greater than x. Put here. Much greater than L means much greater than x also. Then r minus x whole square can be written as r square. Therefore, dV can be written as mu naught by 4 pi twice pi n dx I s square divided by. First, we put here r minus x whole square is equal to r square. Then we made this approximation, that is r is much greater than. Therefore, we can neglect r square in comparison. We can neglect a square in comparison to r square. Now neglect this a square with respect to r square. Now if we neglect a square, then this will be r square to the power 3 by. That means r cube. Or therefore you can write dV equals to mu naught by 4 pi twice pi n dx I into a square divided by r cube. I have to calculate. We have calculated field at P due to this elementary solenoid. Now I have to calculate P, which is on the axis of the solenoid, due to the whole solenoid, can be obtained by integrating this expression between this cell to this cell. That means integrating this expression for the whole solenoid. That means I have to integrate dV from minus L to plus L. X, I have to integrate this over the dx, right? Here S is constant, R is constant, I is constant, N is constant, just one variable here dx. Now I have to integrate dx. The net magnetic field at P will be able to integrate dV, and integration limit will be x is equal to minus L to x is equal to plus L. Now see here, x is from this point. At this point x is plus L. At this point x is minus L. Therefore, I have to integrate x is equal to minus L to plus L dV, which is mu naught by 4 pi twice pi n I square dx divided by r, or we may write mu naught by 4 pi 2 pi n I square by r. All these are constants, so we bring it outside the integration, and integration dx, x is equal to minus L to plus L, and from here we can write mu naught by 4 pi twice pi n I square divided by r, and integration dx is x, and limit of x is equal to minus L to x is equal to plus L. Therefore, B will be equal to mu naught by 4 pi 2 pi n I square divided by r cube, x is equal to plus L minus L. Higher limit minus lower limit. That means mu naught by 4 pi 2 pi n I square by r into 12 right? Now mu naught by 4 pi two L into n into 2 here into pi square into I divided by r. All have written. See here, this is 2, this is 2L, this is n, this is pi, this is a square, and this I divided by r. Now what is this? Right? Total number of turns. Therefore we may write this as mu naught by 4 pi 2 capital N pi square is the area of single coil. Area of single coil, right? Area of the single coil. You write this as divided by r. Now what is this term? L equals to 2L into N, total number of turns. This is total area, this is current. Current into area is what? We have already defined that term. That is dipole moment. Now this can be written as mu naught by 4 pi 2 n by r cube. If we write n equals to n into pi square into I, which is the dipole moment of the solenoid. Now see here the expression. Field at a point on the axis of the solenoid at a distance r from the center of the solenoid is mu naught by 4 pi 2 m by r cube, where m is the dipole moment of the solenoid. And recall your expression From here we can say that a long solenoid or a solenoid can be treated as or can be considered as a bar magnet. A solenoid behaves like a bar magnet. This expression is the same as is the case of bar magnet. Thus, a bar magnet and a solenoid produces similar magnetic field. Right? Similar magnetic field. We have calculated this is for the axial point. You can calculate a field at any point due to the solenoid, and that can have the same value due to a bar magnet.